Hi, welcome to the Calculus 3 lecture series, and we are in the vector calculus unit, and this will be our last lectures about in this unit. So in this lecture is lecture 11, we're going to talk about the diverging series here. Okay, so now let's take a look and go to our lecture notes. All right, so let's see the lecture notes here. All right, so let's take a look at what is the divergence series here and how is that related to the Stokes theory we just did on our previous videos here, right? The Stokes series, we said, hey, if you have a closed bounded surfaces there, and then the surface integrations of the curl of the vector field can be represented as the line integral of the curve bounded by the surfaces here, right? Okay, so the first thing is here. Okay, let's take a look here, right? So this is the same pictures we used for the Stokes series here. Let's take a look at the differences here, right? So the first thing here we see here, so E is a simple and solid here, right? Okay, so let's take a look here. So this is let's highlight the key things, the key word here. So E is a region, is a solid. And then this solid was bounded by the surface S. All right, so that means this is the whole solid things here. The E is this half of the circle, and the boundary is the surface S here. And we have a positive orientation. Now I have a vector field. It's the same vector field, PQ and R. And then also in here we also okay, in here we said we have this is our C, is touch the XY planes, right? So now we said in here, now if you want to take a look, this is the surface integrations, right? For the F, okay? So how do I do that? So how do the surface integrate? The Stokes theory, we say the surface integrations for the what? The curl of the F, right? Okay, so we talk about the surface integration of the curl of the F, and now this is the, the surface integrations for just the F by itself. See here, then what is that? See here, right? Okay, so we said, okay, now this one's here, we say it can be changed to, it's just like the typical classical, like the triple integrations over this solid, right? So what is the, so that's what we say is over this solid volumes here by the divergence definition of the function of the F's here. So that is what is we talk about is the diverging series here. And you will see like some of the, so some of the examples we're going to show, and you will see this will really simplify our calculations here. Okay, so let's take a look at this ones here. Okay, so this one's here, right? So I have this my solid here. So I say evaluate this surface integration of this vector field. So here's my vector field. And then this surface here, right? So this, we say here, this one's here, the surface here is E is what? E is a box, right? So it's a rectangular box here. And now I want to find the surface integrations of F, right? So I want to find the surface integration of F. So as you can see, because this box is here, if we want to use the surface integrations formula, yes, we can do that. So that means you're going to do the surface integration how many times? 6 times, right? S1, S2, S3, S4, S5, S6, right? So each one, we need to find a way to parameterize it, and then you add them together, okay? So it's pretty tedious. It's just like, you know, like if you still remember the Stork series, right? So for example, see here, I think we did like some example like in here, right? So for this surface here, right? So if you want to find the line integrals over here, these triangles, right? If you want to find a line integral over these triangles, of course, you can use the line integrations, but then you need to divide the line integration to how many parts? 3 parts, right? So you have a first curve, second curve, and the third curves, right? So you need to divide it into a 3 part and do the line integration will become pretty tedious. And so that's why we say, hey, in order to do line integration, now I can use the surface integration concept and do the curl of these functions, right? So the same thing here. So now in here, we said, hey, I want to do the surface integration of my vector field, but I have 6 surfaces here. So I need to do the surface integration, each one, or I can use the divergence series. I find the divergence of my vector field, and then I just do the kind of a classical, traditional, like a triple integration over a volume here. Okay, so now let's try to do field. So you will see how do I do that. Okay, so if just do by the surface integrations here, right? Okay, so like if I want to just do by the surface integration, so like we say in here, now let's see how do we do that. Okay, so members here, let's say, okay, let's take a look at the first surface here. So the first surface, let's say, is the S1, is the one facing, right? So it's the one facing the axis here, right? So it's the x equal to 2. So that's the front face, right? So let's take a look at the first number ones here is the S1. Okay, so the S1s here is the front face surfaces, right? So this is a front face surface, and the surface x equal to 2 here. Okay, so remember, right? So what we do, so right now I will do the surface integration of S1 of this vector field of the ds. So remember, right? So we need to do the, you know, we need to do the like the parameterizations, right? We need to do like the R, U, V, and then we need to do the RU and RV, and then this one, we need to do the RU cross RV. So the RU cross RV, if you remember here, right? So we said RU cross RV, really this is what, this is the normal vector, right? So this is the normal vector to the surfaces here. So for these ones here, yes, we can do this all over, but in here, because this is a rectangle, so the one, you know, if you take a look at the face, it's ones, right? So the normal vectors here will be the one directly perpendicular to the surfaces here, right? So it will be kind of like this one is perpendicular to the surfaces here. So what is the normal vectors for the S1? Instead of go through here, we can say the normal vector really is what? The normal vector is will be what? Will be x equal to what? So will be the 1, 0, 0s, right? So will be the this way. So it's only have the I components, x components, right? So this is will be the vector and the perpendicular to this S1 planes here, right? Okay, so now I can integrate that. So now I have the f here. So I will say so my f function, my field is x to z and the y, right? So now this one's here, I can just rewrite this one's here. This is S1. So this will be just the f dot, the normal vector, and the ds is here. Okay, so now let's take a look, see here. So the f dot, the normal vector, is will just be the x to z, y, and the dot 1, 0, 0, right? So this is a dot. So what is here? So this will be, oh, I'm sorry, the f of x, y, z. So here, okay, so this is the f of x, y, z. So x equal to 2, right? Because this is at the face of x equal to 2. So here, this value will be what? This value will be 2 here, correct? And so here, that's why this factor, this value here will be 2, right? Okay, so now you dot product here, this is a 2 here, all right? So now this is here, I can rewrite this one equal to, let me rewrite here, so give them more space here. So this one can rewrite it in here, right? So this is 2, and now because the x is, so the fixed, so I do dz dy here, right? And what is the z? Z is from 0 to 1. And what is the y? From 0 to 3. So see here, you simplify that. So this integration is 6 here, okay? So this is, the side information is 6. Let's take a look at another one. So you will do this 6 times, right? So that's why we say it's pretty tedious. So the S2 is here. Let's see here. Let's take a look at the S2. It will be this faces here is the right faces here. Let's take a look at this ones here. How do we do the surface integrations, right? So this face is here, right? So this is the right face, right? So this is the right face. So this face really tell you y equal to 2, correct? All right. So the y equal to 2, that means what is the normal vector? Is the normal vector will go this directions, right? So it will be perpendicular to this surfaces here. So what is my normal vectors here? So the normal vectors here is only going to what? The j directions, right? So it will be 0, 1, 0, okay? And then now, because the y equal to, so y equal to, oh, I'm sorry, here is y equal to 3, huh? Right, so y equal to 3. So now let's take a look at my f of x, y, z. Okay, so y equal to 3. So this one be x, 2z, and the 3, right? Okay, now I f dot. Okay, so now I will say the f dot normal. So will be x, 2z, 3 dot 0, 1, 0. So what I have here, this is 2z's, right? Okay, if this is 2z, then my integration is here. It will be you're integrating over the surface S2s here. So this will be the Fn ds. So what is the surface S2s here? It's 2z. And now you're going to do dz dx, right? Because y equal to 3. So what is the z here? Z is 0, 1. What is the x here? X is 2. So it's 0, 2. So you integrate that, you will get, okay, so you will get the total will be this ones here. I think I integrated this is 2, right? Okay, so now as you can see for each one, so this is the surface integration for surface number 1. This is the surface integration for the surface number 2, right? So now you can repeat this and add it up. So my final, so let me write here. So my final surface integration for the f, the ds will just be, you add all these 6 together. So I already did that. So this will be 6 plus 2 plus 9 plus 0 minus 2 minus 9. So I'm getting the surface integration for this vector field is 6. So as you can see, that is how do I use the traditional surface integration. Then we say, hey, for this ones here, if this is a solid, right, you can use the divergence series here. So let's take a look at what is the divergence theory tell us, okay? So you will see it's really pretty easy, right? Okay, so the divergence series here. So this is f of x, y, z. My vector field is what is xi plus 2zj and plus y case, right? So you remember what is the divergence of the f here? Divergence of the f is your f here, 2z from the previous definitions, and you dot what? You dot row to the row x, row to the row y, and the row to the row z here. So now if you do that, the dot product, so row x to the x, so it's 1, right? So this is 1 plus row z, row to z to row y. There's no y, so it's 0. Row z to row y, so this is 0, so it's 1. So the divergence is 1 here. So we say, oh, okay, so I can basically integrate over this solid, right? So this is the divergence of the f. You integrate over this volumes here. So you see how simple that is. So this will be the 1. You can say it's dz, dy, dx. So because this is the box, right? So z is from 0 to 1, y is 0 to 3, x is 0 to 2, right? So it's simplified to a very, very easy integration, and it's compared to the previous tedious ones here, right? So that's why it's the 6 here is the same as we did before. Okay. All right, so you see that is what do we mean the divergence theory. You can do you can just use whatever we learn in the surface integration and then try to integrate these 6 surfaces here. Then you add them together. Or you can use the divergence theory and simplify it, right? So you will see how, that's why we introduce this divergence theory, because it's a lot easier. Okay, let's take a look at another examples here. All right, so let's say, hey, let's write to triple integrations for this surface integration. So this is my vector field, right? So this is my vector field. And S is the right triangle surface bounded by the coordinate plane and the 6 plus 4y plus 3z, right? So the equal to 12 here, right? So, okay, let's try to take a look at it. So this one's here, this type error, so it should be 3z. There's no 3z's here, all right. Okay, so this one, we know this surface quite we know this surface very well. We work on that for a long time, all the time here. So let's try to graph this one here. Okay, so this is x, y, z's, right? So the x is 2 here, the y is 3, right? And the z is 4, right? So here we said, okay, so now let's try to graph this one here. Okay, so this is the triangles here, right? So now they said here, be careful of the wording here, right? So they said, the S is the triangle surface bounded by the coordinate plane and this, right? So basically you have like this surface here bounded by the coordinate plane. And so it's really is the surface for this solid, right? So it's a surface for the solid triangles here, right? So now we said, how do I interpret that? So let's say the E be the solid, right? So that's what I graph in the yellow here. So E is the solid region enclosed by the S, right? So remember the S here. So we said that this S here is bounded by the coordinate plane and this planes, right? So this is the, so if you want to do the surface integration, then you can do, well, we have 1, 2, 3, 4. You have 4 different surfaces here, right? So in the ZY, XZ, and XY planes here. So you have 4 different surfaces here. So now let's take a look. We said, okay, well, that is pretty difficult to do here, right? So now let's take a look at my, okay, so now my f of xy, z, so this is xy, y square, and the xz's, right? Then let's take a look at the divergence of xyz. All right, so the divergence of xyz, just take the derivative of the here is by, so remember this is by x, and then the second term is by y, and this one is by z's, right? So you add them together. So the divergence here, so you take the derivative of x, so it's y. You take the derivative of y, so this is 2y. Take the derivative of z is what? Is x here, right? So the divergence here is x plus 3y here. Now you see how simplified that is, right? So your surface integration of the f dot ds. Can you imagine if you want to do the surface integration of here, how many surfaces here you have? You have a S1, right? It's on the XY plane, and you have S2, S3, and you have S4. S4 is here, right? So you have 4 different spaces, and then each one, you need to parameterize it. Sometimes that's not easy, right? Okay, so now we say, hey, the divergence theory tell us, so I'm integrating x plus 3y, all right? And the x plus 3y, and then I'm going to do the dz, dy, dx, right? We did this a lot because we know that this surface here, this is a 6 plus 4y plus 3, so plus 3z's here, right? Okay, so plus 3z equal to the 12. So the z, so if you start with integrating from the z's here, right? So the z, so here this one's z is equal to 1/3. This is 12 minus 6x minus 4y. So z is from where? So z is from 0. So this is 6 minus 2x minus 4 over 3, the y's here. Correct? Okay, so now after that, so you want to integrate the dy's here. So y, that means in here the z is already done. So you have 6 plus 4y equal to 12. Then the y is equal to the 1/4, 12 minus 6 what? 6x here, right? So the dy, you integrate from 0 to where? 3 minus, right? 3/2 x here, right? So that's why now afterward, then you just integrate the dx here. So what is the dx? X is from 0 to 2, right? So as you can see in here, now you change this very, very complicated surface integration to a very typical, it's easy integrations for the like the triple integration in the calculus 2s here, right? So now you can you can take a look at the integrations here and you can integrate that. Okay, so in here, they just asked to write, they did not even ask us to try to integrate that. If you want, you can put this into some integration software and you can get that pretty easily, all right? So compared to you need to do the surface integration 4 times, it's way easier. Okay, now let's take a look at the last problem here. Okay, so the last problem here, so we said in here, okay, so they said Okay, first one here is say find the divergence. So I know the divergence of the f is the first one here, right? So we already learned that. So this is take the derivative of rho x. This is rho y, rho z, right? Okay, so rho x, so it's 1. Rho y is 2y. Rho z is what? 3z the square. Okay, so this is my divergence of the f. Okay, so then the second part, they say write a surface integral for the E, okay, 1 plus 2y plus 3z dv. E is a solid ball in the first octane, all right? So the E is the solid ball in the first octane here. Okay, so now in here, take a look here. So this is what? This is the divergence of the f, right? So this is just, we just defined, this is the divergence of the f. So we say this is the E, right? So this is the divergence of the f. I'm trying to take a look at this integrations here, right? So this one's here will be equal to my surface integrations, right? My surface integrations of the f, right? And the dot what? Dot ds here. So basically, it's like, okay, so you have a ball here. I don't know, I can do that good or not. So you are looking for the first octants. So it's kind of like the over in here, right? So it's very difficult to graph here, right? So it's in the first octants of your solid balls here, right? So if you want to take a look, okay, so basically, then the next things here is really, they said find the integration of the part B here. So basically they said here, you take a look here, right? So for here, you know, if you want to do the parameterization, because I know I can use the sphericals, right? So I know the x equal to the sine u cosine v, correct? And the y is equal to the sine u sine v, right? And the z is equal to the cosine u here, right? It's because rho, because this is a unit, right? So the radius is 1, so the 1 here is all canceled. You know, we did not write it. So then be careful here, u, because this is the first octants, right? So u is only from the 0 to the pi over 2, and the v is also from the 0 to the pi over 2. That's what is your surface was represented here, right? So it's kind of the surface layer. Okay, so now let's try to write it, because after you do this, I can really, you know, okay, so now I know a while ago we already did. So my RU, right? Let's say here. So the name, my parameterize, so R is going to be what? So my R going to be sine U cosine V. We did this many times already. Sine U cosine V, sine U cosine V. Okay, sine U cosine V. And then I have a sine U sine V. We did this several times. Then cosine U, right? And then what are the next things you need to do? You need to do the RU. So the RU is you take the partial for the, for the u's here. So this one is here is a cosine U cosine V. And this is going to be cosine U sine V. This one will be the negative sine U. Then the same thing, you do the partial for V. So this will be the negative sine U sine V. And this one, it will be sine U cosine V. And this one is equal to 0, right? All right, so now you try to do the RU cross RV. So we already did this many times before. So this one will be equal to the sine square U and cosine V to the I components plus sine square U sine V to the what J components, right? And now in here, then plus sine U cosine V to the cosine V's, right? Cosine U and cosine U. Cosine U to the K components. You know, you can use the cross product definition and try to verify it, okay? All right, so now I can find the magnitude of this, right? So I'll find the magnitude of this. So basically, you just the square. So this is a sine square U cosine V square plus sine square U sine V square plus sine U cosine U the square. Okay, and now you will get, it's pretty nice. You got a sine use here. All right. Okay, so now you have here, right? So now you hear your surface integration, right? Now you can just plug all this definition in. So here the F is what? F is, we have is 1 plus 2y plus 3z square. Okay, so you just plug in the 1 plus 2y. So it's 1 plus 2y. What is y here? Is 2 sine u sine v, right? And 3z square. So 3 cosine square u, right? And then don't forget this kind of similar like Jacobian, the sine u. Then you can integrate dv du or du dv, doesn't matter, dv du, because then we say when we do the parameterization, it's 0 to pi over 2, 0 to pi over 2. It is because on the first octants, right? All right, so that's it. And then here, that's what we have here. That is the, you know, the, if you want, you can kind of put into the software and see what your calculator is. You know, what is the integration for here? It is. All right. So that is how do we do, like I said here, right? So that's what is to say, okay, if you want to take this integrations here in this solid and really, you know, it's equivalent to a surface integrations for, equivalent to a surface integrations, right? And then every time when we talk about the surface integration, then you need to do the parameterizations. So this one is not too bad, all right? All right, that's it. And so I hope you know, you enjoyed this divergence theory and make your surface integrations a lot easier here. All right, that's it. And so I guess you know, it's finished this unit, the vector calculus here. All right, okay, nice. You know, let's nice talk to you, and hope you have a good day. Okay, bye.